Fine. So as I mentioned before, typically these have some sort of cylindrical-like, at least the general purpose detectors have a cylindrical-like geometry. And so that usually takes the form of a barrel in the center part of the detector, and then two kind of end caps, one on each side, or wheel regions. And then as you go out of the detector, typical design is to have a tracking detector or a low density detector, which the particles will go through, or most particles will continue to go through, and then a high density detector, which will stop the particles and measure their energy. And so then you also, if you want to measure the momentum of the particle, you'll typically put a solenoid type of magnetic field in the inner portion of the detector. Sometimes this will just enclose the tracking detector. Sometimes it will enclose the calorimeters as well. So we usually call these sort of like an onion-like detector. I kind of don't like calling it an onion because if you look at an onion's layers are all the same, whereas our detectors are different in different layers. So if you've ever had this candy, the everlasting gobstopper, which tastes different at every layer, it's probably a better model to think of. But if we look at the type of signatures that we expect, well, for an electron, because it has charge, if we put some type of material which we can track and the particle as it goes through the magnetic field, we expect to have it bend in the inner detector. And then as we discussed earlier, because of the containment of the shower, it will stop in the first layer of the calorimeter. Photon is similar in its interaction in the calorimeter, but because it doesn't have charge, we won't see a track in the inner detector. Everything is failing on me. Okay, for charged hadrons, again, we will see them in the inner tracker, and then it will start to interact in the calorimeter and have some sort of hadronic shower that starts in the calorimeter. A neutral hadron, again, just like the photon, won't have the track usually, because it won't interact with those, but it will again have a hadronic shower, which is similar in nature to the charged hadron, and it'll have calorimeter information there. And then for a muon, as we mentioned, because it doesn't have the strong interactions, but it does have the electromagnetic ones, but because it's so much heavier than the electron, will kind of barrel through the detector and leave a minimum ionizing signature everywhere in the tracker, the calorimeter, and the muon spectrometer. So if we wanted to measure that charged particle and measure its momentum in the innermost portion of that detector, well, if we had a simple magnetic field, say we had a solenoid, and let's assume that that field is essentially uniform, then you can relate from the Lorentz force to the fact that it's bending and going in a circle. And you can use that if you were able to measure either the radius of curvature or this measure which is called the sagitta, which is the deviation from the straight line path, is another way to do it. We will be able to use this formula in order to calculate what the transverse momentum of the particle going through the magnetic field would be. So as Daniel already pointed out, there's this 0.3, and it just so happens that if you put into the formula in GeV and B in Tesla, then you get a radius out that is in meters, and it just happens to be around this 0.3. Okay, you can go through the numbers yourself. So you can, if you have a small bending angle here, you can then calculate what that is from the geometry and relate it to the radius of curvature. And one thing you can do is you can say that if you measure that angle, then that's a way to relate if you know the length that it goes through the magnetic field, and you can measure that angle, you could find the momentum. Or if you like, you can measure this deviation from the straight line, they call this sagitta, and then calculate what that would be. Again, you can go through the geometry and relate that to the small angle formula, and then using the radius of curvature and relating it to the momentum in the magnetic field, basically determine the radius of curvature or determine the momentum through measuring those quantities. So if you think about it for a moment, right, the bare minimum of points that you need in order to calculate that would be 3, right? Because if you had any 2 points, would just draw a straight line through any 2 points, and any other higher degree polynomial will fit through, of course, 2 points in any one you want. So the bare minimum you want is 3. However, of course, if you have more than that, right, you're going to have more measurements, and you're going to be able to make a more precise measurement of that curvature. And so it turns out that if you use equidistant points, which we don't always do, but if you use equidistant points, you get a formula that looks something like that, which was worked out in the early 1960s. But the main point is that, as you might expect, the dependence on these things is that if you have n measurements, it goes something like 1 over the square root of n is going to your precision of your measurement on that curvature. And you also notice that if you look at the other dependence, it sort of makes sense that the stronger the magnetic field is, right, the more it's going to bend and it's how much it curves. And so it makes sense that that should be in the denominator of that equation. You also see that over the lever arm that you measure it has this very strong dependence. So the longer that you make it, the easier, again, it is to determine how much it bends. It turns out that it goes like 1 over the length squared. Okay, so in principle, if you could make many measurements over a long distance, right, that would be the easiest to be able to see how much it's curving over that. And you also note that, unfortunately, for tracking measurements, the resolution is going to be proportional to that momentum. That is, the higher momentum that it gets, the more difficult it becomes to constrain what it is. So you can kind of intuitively think of that as that it gets to an extremely high momentum, the difference between whatever curvature is in a straight line is very small, and it becomes very difficult to see small deviations from that straight line. Whereas if the thing is bending like huge amounts, right, it's easier to kind of to measure that curvature. So we already discussed that's not quite the whole story, because as well, right, we know that when it goes through that material, well, you put more material there because you want to make more measurements of the position of the particle as it goes through the magnetic field. But the more material you have, or the more measurements that you try to make, that means you give the particle more chance to interact with the detector, and it can go through the multiple scattering. And so it comes in one angle and it goes out a slightly different angle. And in general, that's going to add to the resolution of this, because it's not a simple straight line anymore. It's kind of bending around as it goes through it and changing it. Multiple scattering scales basically with the amount of material. So your ideal tracker then, would have somehow many infinitely thin, measurements of the particle as it goes. It would also, not have things like a beam pipe or a magnet, in the way. So you try to make the beam pipe as small as you can. You usually put the magnetic field outside of the tracker because you want it to bend, for one, and also you don't want to have a material there. And so for a precise measurement of momentum, you want to have as little material as possible. And it turns out this is also going to be important when we get to calorimeters as well, is that you don't want to have a lot of dead material, right? You can't have none, because you need material to support, to hold up your detector, to read out the cables, et cetera. But you want to try to minimize that as well. So in terms of the magnetic field configuration, typically in the inner detector, we'll have like a solenoid type magnetic field. It has the advantage that it's fairly uniform, right? You can make them extremely uniform inside at least the central part of the solenoid. And it has sort of a limited size. When I say limited, right, I'm also showing the picture of what we like to do best as experimenters, is stand on our detector or inside our detector. So these are some people standing inside the CMS magnet, as you can see, which is quite large. And this is some guy standing inside the Atlas air core toroid before they put in the rest of it, which is even, of course, larger than that. Of course, magnetic field lines need to return, right? So you need a return yoke, and the thicker the coil you get increases the material budget in general, if you want to try to make the field stronger. But you also have to compensate that with, you also need to cool it, and it also will increase the material budget in general. So the advantage of this sort of toroid configuration is that it can cover very large volumes, right? This is actually the largest CMS is actually the largest solenoid that was ever industrially scale built detector, magnet. But still, it's much, much smaller than these air core toroids because they don't have to have one gigantic, loop of coil. So the advantage of this is that it can cover large volumes. If here, by the definition, air core, it doesn't have any iron, it has less material. But also, if you imagine what the field looks like through a long solenoid, it's very uniform, kind of easier to understand, right? Easier to calculate what the trajectory of particles would be. If you try to envision what the magnetic field is going to look like for having this kind of crazy configuration of toroids, it's going to be very complicated and non-uniform, which also has its own issues with it. So inside a solenoid field, right, this is the easiest to understand what the trajectory of the charged particle would be because it's just a helix, that is, it's a circle in one direction, and then if it has any transverse momentum to the magnetic field, that doesn't get affected, right, if it's parallel to the magnetic field, and so it just kind of goes along. And so it looks like a helix around that magnetic field. And so you can measure the transverse component of the momentum from how much it bends, or the radius of curvature, and you can measure this dip angle, right, to get the other dimension of that and get the component in the z direction as well. So in general, historically, there have been a number of techniques that you may be aware of. So the older ones, like emulsion, cloud and bubble chambers with photography and scintillators. Due to time constraints, I'm going to talk about just kind of two types of trackers. One is used in most type of modern collider detectors, which for the inner detector is some sort of silicon-based tracking. It has excellent spatial resolution. It's radiation hard. It has highly granular, so it's easier to build detectors with very small features so that you can have excellent resolution on the position of the measurement of the particle. And that's also very good for areas that have a limited amount of area or volume that needs to be instrumented. There is a long, very tradition of gas-based ionization detectors going back over 100 years. Although the technology is older, there are developments. We'll talk about a few of them. But it's primarily useful when you need to instrument a very large area, right, of volume, as you do in muon spectrometers, for example, where you have a lower particle multiplicity and where silicon would just be extremely expensive, right, to put this entire volume outside of silicon. And it also would be a huge number of readout channels to instrument that you wouldn't necessarily need because of the relatively low particle multiplicity in most of that region. So the basics of silicon-based tracking is that this has been used around since the mid-1980s, where you basically take a diode and you reverse bias it, and so that when a charged particle comes through the region here, it liberates electrons and holes in which electrons go one direction and the holes go the other direction. And because of the obvious importance of silicon technology and building computers and building different types of sensors, there's been a large also industry development of silicon-based type of devices. And so individual channels, therefore, can provide approximately 10 micron resolution or so resolution in different forms. So intrinsically, and it's really based on both the inherent technology, but also based on the fact that you build them to be have small channels that are just microscopic features that have different channels that are not very far away from each other. So this can be used to measure the momentum with excellent resolution, and also because of the radiation hardness, you can put it close to the point of the interaction point and get good resolution on where the particles are coming from. Use it as a vertex type of detector to look for particles that then decay to some other type of particles and see resolve that. So in The first type of detectors that were made were the so-called strip type detectors, where they really have one dimension, right? When they measure, basically it's along that particular line, and then you see which one of those lines that you have. But of course, you want to have a little bit more information, because then you would have, however long that line is, right? You wouldn't know exactly where the particle was, and so you'd only have resolution in that one line uh, in one dimension, but not very good resolution in the other dimension. So one way you can do it is you can take basically two of these devices and put them at some angle, right? And so that where they cross, you would get a so-called second coordinate from the detector. However, as you can see here, that also generates basically like what we call ghost hits, because if you have a particle, multiple particles that come through the detector at the same time, there's the real points where the particle came through, but in the case that it hits, here and this strip and this strip, it could either be a real particle here shown in green, or it could be a ghost particle in yellow, just where the two other places where the strips interact. So there are different ways that you can try to minimize that. So you can put it at some so-called stereo angle, and therefore minimize the amount that you have that interaction, which will reduce those ghost hits. But then you have less resolution because of the way that those things intersect. A more general solution to this is the so-called a little bit more modern detectors are called pixel detectors, where rather than being long strips, you just make them short in both dimensions, right? And so they're just like little pixelated points. And so you kind of, from the intrinsic design of the detector, know both of those coordinates to better precision. So in terms of the spatial resolution, we're talking about tens of microns right now in current devices. As we saw from the bib, we also, for either bib type particles or from particles that are coming from multiple interactions or other sources, they tend to have a different time structure than the particles that from the interaction that we're interested in. And so it's also a good thing to be able to distinguish which particles are coming at which time, so you can distinguish between those bib particles and the particles that are there. If you look at how a silicon sensor works, well, the edge of the signal is very, very quick, actually, in a silicon sensor. It's on the order of a sub-picosecond process for the start of that charge collection from the time the particle crosses. However, the time resolution is really determined by when that centroid of charge arrives, and that kind of tells you where the particle was. And then you also have to include information about the noise and the readout electronics and the shaping of the signal, which add also to that inherent resolution. But it turns out that these kind of conventional detectors have on the order of tens of picoseconds intrinsic resolution that we've been able to achieve. So if you look at the evolution of the technology, so in the 1980s, they were constructing silicon detectors for like CDF, for example. And in 1990, they had 50,000 channels, which was covering about 0.7 meters squared. And it took about 3.5 microseconds to read out the detector. And then you can see over time, as the technology, both in terms of the amount of pixelation that has been achieved, that the increased ability to read it out quickly and increase radiation hardness, we've gone from the initial kind of devices that only had to survive sort of kilorad doses to up to gigarad doses for the HLHC and future colliders and megarads. And also the time in order to read out has been drastically reduced from microseconds to about 25 nanosecond time period. And the amount of channels has also grown drastically. So we had initially 5K, 50K channels, and now these HLHC things have nearly 1 billion channels and are reading them out much, much faster. So there's a long history of this. For gas detectors, the detection principle is similar, but a little bit different because of the difference of the medium, where you have a high energy particle that makes some primary ionization. Those primary ionized particles can cause secondary ionization. You collect that charge somehow, and it's and measure it, and that's kind of your source of this. And so you see, for example, here, you can also put it in an electric field and then collect those electrons or measure those electrons rather. And so this goes back, to kind of the history of particle physics. Kind of the Geiger-Muller the counter that you're used to. You see the thing that clicks when you hold it near a radioactive source, right? And that is basically just what we would call a modern-day drift tube that has a gas volume, a wire that's at some high voltage, and then every time particles come through, the voltage is so immediately it goes click. And, you hear it when a charged particle goes through. So that's when the voltage is turned up very, very high. If you put it a little bit lower, you can move it into an ionization or a proportional mode and get a little bit more resolution than just there was a particle, somewhere in that detecting volt. So over the years, they've tried to improve these things. So one thing that you have to do is you have to add these so-called quenching gases because the process is relatively quick and you can cause basically a cascade of raise your signal if the thing is constantly just going off as particles are going through your detector. And so you typically add something that kind of slows down the process. And that's by adding basically polyatomic molecules into the gas mixture that have much more vibrational and rotational modes and allowed some quenching of those showers. So so here is the original Geiger counter type of technology. If you've seen a Geiger counter before, it looks something like this. It's a basic gas particle detector. And then, they were actually used in particle physics for things like discovering some particles, for example, in the muon in cosmic rays, et cetera, right? When you arrange them in a particular order, have a coincidence circuit which says, okay, I have hits on all of these things, it's sequentially, and I'm able to say that this is a particle that came in this direction, and it hit all four of those tubes. So over the years, they've tried to make advancements to improve the resolution. So in the 1970s, there were a big evolution of this. Sharpak won the Nobel Prize, right, for the development of this, of wire chambers, in which you would be able to have multiple wires or wires that were crossing each other in order to improve the resolution and the rates of these detectors. And so you can have gas detectors that are wire chambers that allow a large area and volume tracking detectors. The accuracy is basically a function of the wire distance, and then you can do that over the square root of 12 for a uniform distribution. Charge sharing. And then similar to the silicon, the wires measure only one coordinate. So you can put wires at different angles and play the same game and try to measure the second coordinate as well. One of the more recent things, so the Atlas drift tubes, which are still in use today and are being used to collect data here, is that you have, as the particle comes through, you measure how much time it takes from the start of the interaction to when the signal gets onto when you measure the signal at the anode wire. That gives you a radius from somewhere from that wire of which you are. If you know how fast the signal goes there and knowing the time from it. And so then with pattern recognition, you can work out that I have these bunch of circles of possible trajectories of the muon, and then with particle tracking, you can draw a line that is tangential to all of those charged particles. And modern technology of this is something like the GEMS or these micro detectors. And so in the same way that we've been trying to reduce the size, we're also been trying to reduce the size of the gas detectors. And so by chemical etching processes, you can make very small holes on a foil and that are about 50 microns or so apart, and with modern lithography techniques and then chemical etching. And so then you can basically put a voltage between two conducting planes on this side and that side. and then there's an insulator in between, and there's these little holes that creates a large electric field between the two. And so when the charged particle comes through, you get amplification of the signal through these small holes, and then you can use a PCB to read out the induced charge and get an idea of where the particle came from. And the advantage of these micro pattern gas detectors is that rather than stringing wires, even with the machines that can give you sort of 100 micron resolution, this is done by a modern lithography technique, and the differences between where these little holes are and where the readout is can be on the order then of like 50 microns or so. So it can improve the resolution quite a bit through that technique. Okay. So once you have these basic hits, you have to go from that stage, and then in order to figure out where the particle is coming from and make the measurement of where what the parameters of that track are, you have to go from something that looks like this, right, which is a picture of all the different areas in a particular event, which had hits in the detector of a particular event, to some process which actually tells you, well, which one of all of these hits should be associated to each other, and then how do I extract the parameters after I've done that? So, if it looked like those beautiful isolated events at LEP where you just have one track and nothing else on the whole side of the detector, it's very easy to decide which one of those hits should be associated with a particular track. If it looks like this, it's a much more difficult problem, right? Because you have a lot more possibilities. And so obviously this gets kind of with polynomial complexity, gets more complicated by the number of particles that are there that you have to track, and also the noise. So then once you've decided that you have a set of hits that you want to associate to a particular track, then you have to figure out some way to estimate those track parameters from those set of hits. So in general, this is divided into two components, which one is pattern recognition, and the second we'll call track fitting. And so we'll just deal with the simplest possible ones today. One is basically a road following technique, which is that that the particles that you're interested in come from the primary vertex, right? Come from the center of the detector. So you use that as a constraint, and you say, okay, I'm going to start here, and I'm going to go outward into the first layer of the tracking, and I'm going to find one or two hits in the first or two layers that I could kind of form basically a line for, right? And then I'm going to keep on going outward of the detector, extrapolate that outward, and take a guess, and see if I can collect hits as I go along in that particular pattern. And so this has the advantage that it's relatively simple to construct and to implement. It's kind of the first base of tracking that was started in the 1960s or so. It works very good for cases where there's low multiplicity or general low occupancy. So like if you make a mistake, that's not too many things that you can accidentally collect on your way out. And there's not very much room for making errors. It works less well, right, if you have a bunch of things, if you have a high occupancy and you have a lot of possibilities of trying many of them. And something else that was developed in the 1960s to deal with this problem is called a Hopf transform, after this guy who came up with it in the early 1960s, which is that if we imagine for a moment that over some small enough distance, the particle is approximately traveling in a line, you can simultaneously test for all possible track hypothesis, which is that you can set up a histogram in XY space. And if you imagine that each one of those hits, and you take a point wherever it is, and you connect it in a straight line to the origin, and then that could define a line in so-called rho and phi space, right? The angle and radius space. Point uniquely defines one line, and you do that for all the points that you have simultaneously. And so the point where if it works, the point where they intersect is their shared common line. So they all lie along the same line. And so this will allow us basically to find a set of hits that are all on the same line. and basically connect them together that way. So there are more complicated versions of this. So there's a whole industry of algorithms who have gone out in a way of thinking of this. The most modern way of doing it is using AI techniques, which you throw in some very complicated, pattern recognition, the same type of thing that's looking to do driving and stuff like that, right? And doing identification of patterns. So once you have that set of parameters, you need some way in order to figure out what the parameters are that you want to do. So the simplest way to do it is to put it in some sort of chi-squared where you have a prediction based on a particular model, a track parameter. So if you think it's going in a circle, for example, or a helix or a circle in the transverse plane, you can form a chi-squared, which tells you something about the track parameters, and then you can see how much the particular set of hits deviates from that, and you can then minimize the chi-squared along with the prediction of the model, where the actual points are and the individual measurements are. So it's basically the standard form of a chi-squared that you've done for like fitting lines and other things like that, and you can fit for the measured parameters. So how to optimize a tracker? Well, in order to get good resolution, you would like to have as large as possible magnetic field and as large as possible volume as possible in order to optimize the resolution. You would also like a large number of measurements with excellent per point resolution and a small amount of material. In order to get good resolution on the impact parameter or where exactly the comes from, you would like a small beam pipe, and you would like the high precision detectors to be as close as possible to that interaction point. So you can think of it, as an extrapolation problem, right? If all of your measurements are way out, you're trying to extrapolate all the way back to the other side of the room. Relatively small errors on these individual measurements can make when you extrapolate all the way out to the other side of the room, makes a big difference. Whereas if your measurements of the trajectory are right next to where the particle comes from, right? They don't grow with you don't have to extrapolate as far. And so what you'd like to do, therefore, is put as many of those precision detectors as close as you can to the interaction point to basically get that best precision. Of course, that's where the radiation is the highest, and that's the challenging point. You would want to have good acceptance, basically instrument as most space as you can in order to see the particles don't have giant holes, right, in the detector. You need some. There is going to be a transition region between the barrel-like detectors and the end cap-like detectors. You need space for readout and cooling, and the beam pipe, of course. And you'd like it to be robust against high occupancy. That is highly granular, basically as small as you can make those individual measurements, right? And of where it is. And you want it to be fast as to not record unrelated particles, right? Not ones that are many beam crossings. Factors that you have to take into account. That is, the more channels that you add, the larger the detector that you make is going to cost. You're going to have more readout electronics, cable, and data acquisition. You also need to have a support structure. You also need to have cooling, data readout electronics, radiation hard, and you also want to have some built-in redundancy because you may be operating the detector for years at a time without being able to access it. Part of it breaks, you want to be able to still measure the particles there, and so you need to have some sort of redundant system. So if you look at how the resolution of tracking evolves, it has several components. So typically at the very low momentum, energy loss fluctuations and multiple scattering are going to dominate that resolution because a very relatively low energy particle, it's leaving, as you remember in the beta block distribution, if you're really low on that, your energy can be quite large that you leave it there. And it can scatter quite a lot as opposed to being a very high energy particle where it just kind of barrels through whatever material there is there. At high momentum, those things very rapidly drop off. As you saw, here's the blue line is the energy loss fluctuation, and then the multiple scattering here is Rand also falls off. But you see that this other factor increases quite a lot. And so that's basically the intrinsic curvature problem that is it's getting straighter and straighter. It becomes more and more difficult to see the difference between that and a straight line. And things like the intrinsic resolution of the detector and the alignment become the main contributors. And so as an example, for the Atlas muon spectrometer, which I've worked on for a number of years, the goal and eventual, what we actually achieved was where something was over the tens of meter scale on the order of the thickness of a hair, right? And in order to achieve the resolution that we wanted to. So, but by some very complicated system. So that becomes very difficult. And you notice in general, it's hard, there's just basic physics, which means that the momentum resolution is going to degrade as you get to higher and higher momentum. So if you take a look just briefly at a couple of these designs, the CMS inner tracker looks something like this. So it has a very strong magnetic field, a 4 Tesla. It's very uniform throughout the entire thing. And you see that it has these pixel detectors, which are the most precise granular detectors, and they're very, very close, right? And to the interaction point, it's a very small actual volume compared to the entire of CMS. And then you have a strip detectors as you go out in these discs, and as you go out here, also in both the barrel and the discs. And so the performance varies depending on how much curvature you get in the, but it's excellent in particular in the center part of the detector where you get a lot of curvature because the particle is, most of its momentum is transverse, and you have excellent coverage of all of the systems there. But you see that's 200 meters squared of silicon, and it's on the order of 70 or so million readout channels. If you look at the Atlas muon spectrometer, which is the last slide I will show before I let you go to lunch, is that so this is kind of exactly the opposite idea, right, of the inner tracker, which is this highly granular, millions and millions of channels that are very close up and trying to instrument as precisely as possible this tiny, tiny space. Whereas the Atlas muon spectrometer is humongous, right? So I don't know if there's people, they didn't draw them in, but they're like this thing is like 10 meters long or something like that, right? So people are very small on this scale. So there's tremendous volume, right? It's a huge area that you're trying to instrument. It's 10,000 meters squared. And in order to get to that precision, you need to be able to have a very high involved internal alignment system, and you're using gas detectors basically over the entire thing, because otherwise it would be prohibitively expensive to try to put that with silicon or that large of a volume. It would be I don't know, billions of dollars or something, right? Okay, so I hope that gives you an idea of where kind of the trackers lie, and then tomorrow we'll talk about calorimetry measurements.